that there are compounds that are called microtubule inhibitors, or we'll just call it MT. What if we could deliver that microtubule inhibitor into that cancer cell very specifically, and it binds to these microtubules, and what it's going to do is it's going to break them apart. If it breaks them apart, then there's no way for that cell to take the chromosomes and pull them to either end. If that can't happen, you're not ever going to get this. You will never allow that cancer cell to divide. So, how do we use that knowledge? Let's come back to the SMDC approach. We have the 4 modules. Here's an actual drug that about 400 people were treated with. Almost made it to become a full-fledged drug. This is called pentaphalide, folate. And on this end, see this in red? This is generically called a vinca alkaloid, vinblastine analog. That is a microtubule inhibitor. When we take animals, in this case have a tumor, if we don't treat that animal, that mouse, with anything, but we measure the tumor on the back, it grows until the point when the animal dies. On the other hand, if we treat that animal with just the vinca alkaloid, no targeting, just a free poison, if you want to call it that, sure, there's anti-tumor effects. So we're measuring the size of the tumor. The tumor in the green curve is going down. And in this case, this animal was treated at the maximum tolerated dose level. We couldn't give any more. And what you saw is, okay, the animal had some benefit, but guess what? It all came back. That none of them were cured. On the other hand, if you target that drug, which is in red, you have a folate conjugate of that drug. Not only did we see anti-tumor effect, but those tumors disappeared and never came back. And that was treated at 1/5 of the maximum tolerated dose. And what you can see is that looking at animal weight was just as kind of a gross measure of how bad they felt, or was there any toxicity. In red, which is our targeted drug, there was no weight loss. That's the goal. If your grandmother's going to get treated with a drug, you don't want grandma to get sick. You want that tumor to disappear without her getting sick. That's the goal. Well, that happened in this mouse here. When you treat with the untargeted drug, look at all the weight loss. When an animal like a mouse loses weight that fast, it's feeling crummy, it's sick. And there's other things going on, which we won't go into detail, but nonetheless, that animal is very sick. And so it's a stark difference, it's a contrast between targeting versus not targeting. And what that looks like is, here's 3 mice, and see this big ugly thing here? Looks like luggage on the back. That's the tumor. That's the tumor that's overtaking their body. You treat with the targeted form of that drug. Here we go. And you can eliminate those tumors in those mice. All that's left is a mature scar from where that tumor used to be. So, very successful application of targeted medicine. Sorry, I have a little bit of delay here. There we go. Now we can have fun with this. Remember how I said there's 4 modules? Well, I gave you an example of a microtubule inhibitor. That stops cell division. Well, you can also stop cell division if you attach a different drug. And here's just, I know it looks pretty ugly, but it's actually not that bad to make. But this is a very potent DNA crosslinker. So another target inside of a cancer cell is to prevent the DNA from unwinding so it can't replicate. And in that setting, we also see curative activity. In fact, in this model that we tested, that same drug that cured those other animals, the microtubule inhibitor, well, it had some anti-tumor effect, but against this particular tumor, it didn't cure. We had to switch it to a DNA poison before we cured it. So that's the fun we have, is trying to understand the best approach on how to treat. So towards now the end of my talk, what I want to do is give you 2 examples of what we're doing currently in the clinic by treating patients. And this is sort of state-of-the-art stuff. If what I just talked about wasn't interesting, hopefully you'll gather something out of this. This is radioligand therapy. You're going to hear a lot more about this. Now, radiation and whatever gets a bad rap sometimes. If you can control it and deliver radioactivities precisely to where you want it, in other words, precisely to the tumor, the radiation that's emitted will kill that tumor. And so that is the idea behind what we're doing here with radioligand therapy. And we have one that's in the clinic right now. It's actually in phase 3, where we have not folate, but we have another molecule that actually homes to prostate cancer. On prostate cancer, there's another protein. It's called PSMA, prostate-specific membrane antigen. And we have a small molecule that binds. The small molecule is the key, and that PSMA is the lock. But instead of attaching a microtubule inhibitor or a DNA poison, we attach instead something radioactive. And this is lutetium-177. Lutetium-177 is a beta emitter. So as it decays, it releases a beta particle, and it's a high-energy electron. Think of it that way. So what? What does a high-energy electron do? Well, if it gets into the cell and it gets close to the DNA, it's going to screw up the DNA. And how it does that is it can cause a single-strand break or a double-strand break. Now, many cells have the ability